Morning session. Welcome everybody to this Friday morning session of the Applied Category Theory Conference. My name is Rick Boot. I will be the host of this session. Just a few minor technical points. Please make sure that your microphone is on mute before we get started. But if you do have a question, please feel free to raise your hand. So there is a raise hand button on the bottom of the screen where it says reaction. If you click on reaction, and then just under that, it will say raise hand, and I will try to keep an eye out for all questions. And questions are desired because this is a math conference like any other math conference. So we'd very much like to have questions. This talk will be 40 minutes long. That's including question time. So without any further ado, let's get started. So our presentation today is on the topic of commutative monads for probabilistic programming languages. The paper is by Xiaodong, Bert, Lindenhovius, Mike Mislove, and Vladimir Zamdzhiev. And Vladimir will be our speaker today. So over to you, Vladimir.
Okay, thank you for the introduction. First, can you see my slides? Everything is okay?
Yep, we can see them.
Okay, great. Okay, so I will start with the motivation. So we're motivated by the fact that, well, we like probability and recursion, and we want to study both effects denotationally. It's a very natural combination because it allows you to, for example, if you have a probabilistic algorithm, it allows you to just repeat the algorithm until you find the correct solution. But now the question is, how can we study this denotation? Now, as far as recursion is concerned, the answer is clear. It's given by domain theory. This is, the classical approach. It's a very successful theory, and it allows you it provides the semantics for recursion. However, if you wish to add probability to the domain theoretic approach, well, historically this has been difficult, and this has raised some big problems. And the classical approach here is given by considering the valuations monad of Jones and Plotkin, which was described at LIX 32 years ago. However, there are two big problems which have not been solved since then. And I think this is one of the reasons why other experts have considered other denotational approaches for solving this problem, and some of those include probabilistic coherent spaces, quasi-Borel spaces, measurable combs, but also others. So here in this paper we presented it at LIX a few weeks ago. We were motivated by the fact that, well, actually we want to combine probability and recursion using the domain theoretic approach in an elegant way, and to show that actually it is doable. So this is our motivation.
Hi, Vladimir, it's Jamie. Are you going to actually tell us what the two major problems are, or maybe you already said?
I will later, but I need some background first.
Dramatic tension. Okay.
Yes. Just building up the tension. Yes. Okay. First, to explain the problems we have, we need some technical background. So we start with domain theory, and so brief introduction. So the main idea of domain theory is that it gives you an order theoretic view of computation and recursion. And in particular, there are two main objects under consideration there, which are DCPOs and domains. Okay, so DCPOs are a larger class, and they're defined in the following way. So first, you have to introduce the notion of a directed set, which I think is well known. It means that basically, if you have a partially ordered set, then every two elements in the directed set need to have an upper bound within the directed set. And then a DCPO, it stands for a directed complete partial order. And this is just a poset where every directed subset has a supremum or has a least upper bound. An obvious example is the real unit interval, which is a DCPO when equipped with the standard order. Another example is given by the open sets of a topological space with respect to the inclusion order. Okay, the appropriate notion of a morphism between DCPOs is given by the notion of a Scott continuous function, which is just a function which is monotone and which also preserves supreme of directed subsets. so the category of so basically DCPOs and Scott continuous functions form a category which we indicate with DCPO, and this category has very nice properties. It's complete, it's co-complete, and very importantly, it is Cartesian closed. So this will be important for our talk. And in general, this category is very important for semantics. Now, a smaller class of objects in domain theory are the domains, which also gives the name to the theory. And basically, the way we can think of domains is that they're very nice and very well-behaved DCPOs. So in particular, you can define an additional notion there, which is another relation, which is the way below relation. You say that an element X is way below an element Y. If you take a directed subset whose supreme is above Y, then it means that there has to be an element of the directed set which is above X. And this actually implies that X is smaller or equal than Y. Now we use this notation to indicate the set of all the elements which are way below Y. And then you can, using this, you can introduce a notion of a basis, where the idea is that a basis is a subset such that it has the property that every element of your DCPO is a directed supremum of all of the elements which are simultaneously in the basis and are also way below your chosen element X. So a basis does not always exist of a DCPO, but if it does exist, then the DCPO is said to be continuous. And in this case, it is also called a domain. Okay, so this is a domain. So it's just it just gives you some additional structure that you can work with. They have nice properties, and from an individual perspective, they have more structure than a DCPO. However, from a collective viewpoint, the situation is not ideal because the category of domains and Scott continuous maps is actually not Cartesian closed. Okay, so this is a problem that will arise soon. It will manifest when we talk about probability. Another notion that we have to introduce is the notion of the Scott topology. So in particular, every DCPO can be equipped with a canonical topology, which is called the Scott topology, and it consists of the subsets of D which are upwards closed. This is the first requirement. And the second requirement is that every such subset is inaccessible by the directed supreme. So it means that if a directed supreme is contained in your open set, then it means that there must be something from your directed set also in your open set. And these sets are called Scott open. This topology is canonical because if you're given a function between two DCPOs, then this function is called continuous in the order theoretic sense, if and only if it is continuous in the topological sense when the two spaces are equipped with the induced Scott topologies. Okay, so how do we, so far, I didn't say anything about probability. So how do we add probability? So with this, we can talk about recursion, but for probability now, a natural question is to ask is, well, why not just use measure theory here and just take some sub-probability measures on the induced Borel sigma algebra by the Scott topology? Well, I think it's a natural question to ask, but then if you consider this assignment, basically which assigns the space of measures, it's unclear how you can get a monad over DCPO using this, and because of this, you get in trouble with, you won't be able to have a nice semantics, I think. So this is why what people have done. So this was, this was first introduced by Claire Jones and Gordon Plotkin in LIX 1989. Is they introduced the notion of evaluation. Okay, so evaluation is very similar to a measure, but it's not exactly the same. So what is evaluation? Okay, so this is the definition. So a sub-probability evaluation on a DCPO is just a Scott continuous map from the set of Scott open subsets of X into the real unit interval, which satisfies two additional conditions. So the first condition is that it's strict, which means that if you measure the empty subset, then you just get 0. And the second condition is modularity. And basically these two conditions here allow us to talk about probability. I mean, see that both equations are indeed very natural to assume. So the simplest possible valuation that you can think of is just the constantly zero valuation. It just assigns 0 to every scope open subset. And slightly less trivial one is given by the direct valuations. So if you choose an arbitrary point of your DCPO, then the direct valuation at X is just it just performs a membership test. So if if the point X is contained in a scope open subset, then you get 1. Otherwise, you get 0. Okay, so it's similar to direct measures. It's fully analyzed. Okay, so what is nice here is that if you consider the set of all valuations over a DCPO, this set is denoted by V of X. This actually forms a pointed DCPO when equipped with the stochastic order. So the stochastic order in this case is pretty obvious. I mean, you just compare the valuations pointwise, where in this case your points are just the scope open sets. So it's a very natural order. And the least element is, of course, the always 0 valuation. Okay, so you see that valuations are somewhat similar to Borel measures, but they're not the same because we define the valuations on the scope open subsets, whereas a Borel measure is defined on the Borel sigma algebra induced by the topology. So it is not the same, but in some cases actually they coincide in the sense that you can extend the valuation to a measure, but this is true only sometimes. In general, it is not true. Okay, good. So our motivation for this is to extract a monad somehow. So now I will explain how this indeed determines a monad. So basically, we can get a strong monad over DCPO when we equip it with the following structure. So first, of course, we have to explain how you get a functor out. So if you have a Scott continuous function from D to E, then V of H, which goes from the VD to VE, can be defined by just taking the push forward valuation of H against mu. Right? So if you know measure theory, this is one of the first constructions you see. It's just the push forward, and here it also makes sense. The unit of the monad is pretty obvious. You just send a point X to the direct valuation at X. So this is pretty self-explanatory. Now for the multiplication, here you have to do a little bit more work, because first you have to introduce a notion of integration. So the way that this is done is that if you're given a valuation nu and a Scott continuous function from X into the real unit interval, then the integral of f against nu is given by the following formula here. So the left-hand side is just the notation we use for the integral, and the right-hand side is a Riemann integral where t ranges from 0 to 1, and this is the function that we are integrating. So this makes sense because this half-open interval here, t1 from t to 1, is Scott open in 0, 1. And then under the inverse image of f, you get a Scott open subset of x, and then you can measure this using the valuation. So this integral actually makes sense. And then the multiplication is given it's just computed using the integral that we just defined. So if you have a valuation over the space of valuations, you can just get a valuation over this space by integrating over all the possible valuations that you have here and measuring u. And so that's it. And using basically a similar idea, you can then also define a notion of a strength for this monad, where this time you integrate the characteristic function over of a given Scott open subset in the product. Okay, so these technical details are not so important for the talk, but I'm just showing you that it's a very natural way to define the monad structure, and it's similar to what you can see in measure theory, in particular to Giri monad there. Okay, now what are the problems? So Jamie was asking. So of course, here's the whole slide, and here there are big problems. So let's start here with the last bullet. So if you actually want to have a nice semantics for probability and recursion, then it's well, let's say nice and elegant semantics. Then what you want is to have a commutative monad over a Cartesian closed category. Okay, so if you have this, then you can describe a nice mathematical interpretation of a programming language. But how do you do this? Okay, so let's say we use the monad V on DCPO. So we know that DCPO is Cartesian closed. So okay, one requirement is covered, but then for the past 32 years, no one has proven whether V is commutative or not on DCPO. So this is unknown, like nobody knows. There's no counterexamples, there's no proofs. So okay, the first obvious approach fails. Now the second approach is to take, so V is also known to be commutative on domains, on the category of domains. This was shown by Claire Jones in her thesis. But as I mentioned, the category of domains is not Cartesian closed. So there is now a second problem, which has a name. It's the Untitled problem, which therefore means it's much more complicated than the previous problem, which doesn't have a name. And this is to find a Cartesian closed category of domains on which V is a commutative monad. Okay, so here, these are the two big problems, and they are, they're very hard. These are very hard problems. Now, however, so this is, if you wish to have such an elegant semantics, then, this is, I think, the two first, approaches that you can probably think of. But now what we're going to do is something different. So we will explain how you can get a nice semantics while ignoring these problems. Okay. Now, how do we ignore them? Okay, so our goals are the following. We need a commutative monad of valuations over a Cartesian closed category. So the main idea is that we're going to take a submonad of the valuations monad, where we're only going to take the valuations that we need. And the ones that we don't need, well, we don't care. They're outside of our monad. So in particular, we do the following. We describe a commutative monad of valuations, which we want to call M, on the category DCPO, which is Cartesian closed. Okay, so, and in fact, this M is a submonad of V in the sense that well, for every possible choice of a DCPO, M of X is a subset of V of X. So we only take some of the valuations. And moreover, the natural transformation, which is determined by these inclusions, is a strong map of monads. So basically, the monad structure of M is exactly the same as that of V. So it really is a submonad in every sense. Now, we also prove that M is the same as V on domains, and this is important because everybody agrees that the action of the valuations monad on domains is ideal. So in this case, okay, we do the same thing, but in general, it's it's only a subset in general. Okay, and we will show that we do have enough valuations for semantics by providing a sound and adequate interpretation of a language called PFPC, which is it is a very expressive programming language with discrete probabilistic choice. As a bonus, we also characterize the Allenberg-Moore algebras of our monad M over domains. And well, in this case, I said that it's the same as V. So basically the two Allenberg-Moore categories in this case are the same. And we show that they are isomorphic to the category of continuous Kegelspitzen, which was introduced by Klaus Keimer and Gordon Plotkin. Okay, and actually this corrects an error in the thesis of Claire Jones, where we have a counterexample in the paper if you want more information. And as another bonus, well, actually, we introduced 2 more commutative monads that satisfy all of these properties here. And those are constructed using topological methods. However, I will mostly focus on the M monad because it is the simplest one and the easiest one to understand. Okay, cool. So what's the deal with commutativity? So the commutativity of the monad V is actually, when you write out the equations which are required, it turns out that this is equivalent to proving the following Fubini-style equation for every possible choice of DCPO's DME. So this is the spaces over which we're integrating, where here the characteristic function of U is taken for a Scott open subset in the product, and where the valuations are arbitrary. Okay, so again, we don't know if V is commutative, so this equation has not been demonstrated to hold in general. However, we do know that this equation holds in many special cases. So in particular, there is a class of valuations which are called simple, and I mean, they really are simple, where if you choose one of the 2 valuations here to be simple, then basically the integral, it collapses to a sum and it becomes easy to prove. Okay, so for simple valuations, it is true. And then it is also true for directed subprime of simple valuations, because so the integral is Scott continuous in the valuation component. And then this allows you to also prove it for this class. And then you can then take another directed subprimum on top of this and so on. So we could do this transfinite. So in these cases, we do know that it is true. And this is actually one of the motivation for construction. Okay, so what is a simple valuation? Well, first, it's kind of obvious that valuations have a convex structure. So if you choose probability weights, so these 2 requirements here just tell you that, okay, you can choose some finite number of probability weights and some finite number of valuations. Well, then the convex sum of these valuations is again a valuation which is defined in the obvious way. You just define it pointwise using the convex structure of the unit interval. And this is a valuation. And now a simple valuation is one which is just a convex sum of Dirac valuations. Okay, so that's it. It's true to its name. And we shall write Sx for the set of simple valuations. So indeed, Sx is a subset of V of x. However, this is not a DCPO in general. Okay, so it is not closed under directed subprime. Another motivation for main definition is the following. So if you actually wish to talk about discrete probabilistic choice in a programming language, then you really need 2 things. First, it's kind of obvious that you need the simple valuations, because otherwise, I mean, you can't really say anything. I mean, you won't have any kind of convex structure in there. And 2, because you have recursion, then you also want to be able to take subprima over such valuations. Okay, and this basically gives you enough. So this together with the previous, Fubini observation motivates our definition, which is the following. If you take a DCPOD, then we define MD to be the intersection of all sub-DCPOs of VD that contain the simple valuations. So this is equivalent to saying that MD is the smallest sub-DCPO of VD that contains the simple valuations. So that's it. That's the whole definition. Now, if you do some more work, you can then prove that that the above assignment in fact extends to a commutative monad on DCPO when it is equipped with the monad operations of V. Okay? So the monad operations are defined in exactly the same way. And actually, most of the proof is to show that, well, they restrict as required. And then commutativity holds by what I said on the Fubini slide. This is basically the main idea. Okay, so now you have a commutative monad over DCPOs, so not bad. A natural question to ask now at this point is whether this is the DCPO completion of the simple valuations. but this is not true. It's not true, and in fact, it is a topological completion of the simple valuations within a larger space. So you see that, its definition here, it depends on the larger space VD, whereas the notion of a DCPO completion, it's universal. It doesn't depend on another space. So it is. So, okay, so how do we understand M as a topological completion? So to understand this, we have to introduce a different topology on DCPOD, and this is the D topology. So the D topology on D is the topology which is determined by, it's the topology where the closed subsets are just the sub-DCPOs of D. So that's it. And then the D closure of some subset within DCPO, it is just the topological closure of this set with respect to the D topology on D. So an equivalent way of defining the object mapping of M is to say that MD is just the D closure of the simple valuations within the space of all valuations. So that's it. And now this gives you a universal property, right? So, I mean, from topology, you get a lot of nice results about the closure of a space. And actually, this is a lot more useful if you want to do the required proofs. So, on the previous slide, I showed you the simplest definition because it's easier to understand. But for the proofs, this view is better. And okay, so here we see that there is, one notion of a completion, or which works, which is the decompletion or the declosure. But actually, this can be generalized, and there are two additional completions of the space of simple valuations that we know of, which also will give you a commutative monad. Okay, so this I will talk about this now. Here, this is a little technical, so I will only introduce the main idea. So I definitely don't have time for the details, but the main idea is the following. So there is a notion of K category, which is introduced by Kamo and Lawson, I think. And the idea there, the idea of a K category, is that it allows you to determine a completion of each K object. It allows you to determine a completion of each T0 space as a K object. Okay, so this is the main idea there. Where so T0 here is the space of T0 spaces, so they satisfy the Kolmogorov separation axiom. So I won't give you the details, but I'll give you all of the examples that we know work for us. So in particular, if you could take the category of D spaces and continuous maps. So this is what I talked about on the previous slide. Another example is given by sober spaces and continuous maps, which is a subcategory of D. And then you have well-filtered spaces and continuous maps. And our most general theorem says that if you have a K category, which is a subcategory of D, well, this actually determines a commutative monad of evaluations on the category DCPO. And in fact, M is just a special case of this theorem, where the choice of parametrizing category is just D. Okay. Now, of course, I described it in a simpler way because this construction is a little technical, but it is in fact a special case. And here we only know of 3 K categories that satisfy these the requirements of the theorem, and because of this we have 3 commutative monads. But if in principle, if somebody finds another K category which satisfies these conditions, then this will give another commutative monad. So what can be said here is that M, so if you use this construction, then M is the smallest possible commutative monad which arises from this theorem. And at the other extreme is the monad P, which is given by taking the subrification of spaces. This gives you the largest possible commutative monad, which can be obtained using this theorem. Now, if you use other methods, then maybe there are more. And well, all of these monads are actually submonads of V. However, the middle three here, M, W, and P, are commutative, whereas for V, well, we do not know if it is commutative. And now everything else that I'm going to say holds for M, W, and P for all the three commutative monads, but I will focus mostly on M. Okay. So one of our results is to characterize also the Eilenberg-Moore algebras of our monads over domains. So actually over DCPOs, we have not done it. Like we do not know what they are, but we can do it over domains. And the answer there is that they're just continuous Kegelspitzen. So I will just introduce this notion now so that you understand what's going on. So first is the notion of a barycentric algebra, which is just basically a set with a convex structure. So the main idea is that you have this operation here, which is parameterized by a choice of a real number between 0 and 1. And the way you may think of this operation is that, well, if A and B are vectors, then you may think of A plus RB as being R times A plus 1 minus R times B. So this is the intuition. And then these equations here, they actually axiomatize what the operation should do. But if you think of it as the way that I just said, then these equations are pretty obvious. But it is weaker than a vector space because here we don't really have scalar multiplication, and our only scalars are between 0 and 1. And even then, the sum is only sometimes defined. You cannot just take arbitrary sums of vectors. So the proper axiomatization is the one provided here. Okay. Now, a barycentric algebra is pointed if you have a distinguished element bottom. And we will see on the next slide that this will be the least element. And then you can, if you have this distinguished element, then you can define a scalar multiplication with a real number between 0 and 1 by just taking the convex or by just taking the barycentric sum with respect to the scalar R and this distinguished element. Now, the proper notion of a morphism between barycentric algebras is given by the linear maps, which are maps that preserve the distinguished element, and they also preserve the barycentric sums. Now, finally, a Kegelspitz is just a pointed barycentric algebra where the barycentric sums and scalar multiplication respect the order. Okay, so it's a barycentric algebra which has the structure of a DCPO, and this function here is called continuous in the A and the B components, and scalar multiplication is also called continuous in both components as well. So that's it. And in a Kegelspitz, you can prove that the distinguished least element is in fact the distinguished element is in fact the least element of the Kegelspitz. So it is always pointed. So in general, we may think of Kegelspitzen as just DCPOs with a convex structure. So that's it. And they were introduced by Caimont and Claude. Examples are the real unit interval, and also both MX and VX are Kegelspitzen. If in addition X is a domain, then the two are equal, and you get the continuous Kegelspitzen in this case. So we have a theorem in our paper, which is that the Eilenberg-Moore category of M over domains is isomorphic to the category of continuous Kegelspitzen and Scott continuous linear maps. So actually here I forgot to say that, that a Kegelspitz is continuous if it is also a domain. So not just a DCPO, but a domain. Right? So this is the theorem. So we have isomorphism of categories here, and this is good. And as I said, M and V are the same on domains, so the two are equal, the two categories are equal, and this corrects an error in the thesis of Claire Jones. Okay, so this part here I am going to skip because I'm short on time, but basically in a Kegelspitz you can define general convex sums like this. So these are finite convex sums but you can also define countable convex sums as well. Let's keep the details. Now, a final contribution is for semantics. So here we consider the classic category of M, which has over DCPO, which has nice structure because it inherits the co-products from DCPO. It has a symmetric model structure because the monad M is commutative. And it also contains a classically exponential because the base category DCPO is Cartesian closed. It's also enriched over Kegelspitzen, and basically all of the data is also DCPO enriched, which is nice. And we can solve recursive domain equations within the category. So the main semantic results is that we have a sound and strongly adequate interpretation of the language PFPC, which is a language that has function types, pair types, sum types, and full recursive types. So here we allow a recursion. So here type recursion allows the use of function spaces, and this in turn induces term recursion. And okay, so the main results are soundness, which is the left equation here. It just says that the interpretation of a term is can be recovered as a convex sum of its single-stepped redux. And the second equation, which is a lot more complicated, this is a strong adequacy. So this equation is like 16 pages. The proof is 16 pages in the appendix, so it requires a lot more work. It shows that the interpretation of every term is a potentially infinite convex sum of all of the values that it could reduce to, where the probability weights are the probabilities of reduction determined by the operational semantics. This is also true if we replace M with our other two commutative monads, P or W. Okay, so to conclude, because I think out of time almost, we have described three commutative submonads of the valuations monad V of Jones and Plotkin. We have characterized the Ehrenberg-Moore algebras of the monads and also of the valuations monad on domains. And they're given precisely by continuous Kegelspitzen, which are described by Keimel and Plotkin. And we have a sound and strongly adequate semantics for PFPC using our monads. Okay, so for future work, so here we have talked about discrete probabilistic choice. But what do you do with continuous probabilistic choice? So here the situation is a bit more complicated. So actually, we don't know if you can have a nice semantics using our three monads. But actually, recently we discovered a fourth one, which is commutative, and this one is constructed using algebraic ideas. It's bigger than the three that we had before, and in fact, it's as large as V if and only if V is commutative. So since this is a big open problem, we think that this basically shows it's probably very big. And we have some reason to believe that this could be good for continuous probabilistic choice, but this is work in progress. So we'll see in the future. So thank you for your attention and for giving me the opportunity to speak here.
Thank you, Vladimir. So if you're participating electronically, there is an applause button that you can hit under reaction. So let's all electronically applaud Vladimir for a great talk. And I see multiple people who want to ask questions. We'll go with Tobias first.
Yeah, thank you. So there's a nice submonad of V consisting of continuous valuations, right? I wonder how that fits into your chain of submonads. And also what the status of its commutativity is.
A submonad of continuous valuations. So what do you mean by continuous valuation?
It's not continuous valuation.
Well, okay, but here the notion of valuation that I introduced, it's so here it is Scott continuous. Right?
Oh, sorry, I missed that. So yours are Scott continuous to begin with.
Yeah.
Okay. All right. Yeah. Thank you.
Sure. Andy, go ahead. Andy, we can't hear you.
We have a question in the audience here. Maybe we could take that.
Okay, so let's go to the audience. Maybe Andy can figure out what's wrong.
Hello, Vladimir. Very nice talk, by the way.
Thank you.
Two questions here. So first, your monad M, does it solve the Jung-Tix problem? So does it restrict to the continuous domains? And the other question is if it, I don't know if you said it, and does, is there any reason why you didn't define it as a Scott closure, but as instead you define it as a D or closure in the D topology? So,
Sure, okay. So we have definitely not solved the Jung-Tix problem. So it is not a solution because here so the Jung-Tix problem is really about domains, right? Here we have not said anything new about domains, really. We have not found any new Cartesian closed categories and so on. So no, we will not solve the Jung-Tix problem. Why we don't take the Scott closure? Basically, the proof fails, so you cannot. So here, well, so when I can't find this slide. Okay, so basically, if you take the Scott closure, I think we tried this, but it does not work. It does not give you the required closure properties here. I don't remember what exactly was the problem though, sorry, but it definitely does not work. So you have to take the declosure, it's the more appropriate notion.
okay, thanks.
Andy, you want to try again?
Working, by the way.
Yeah, we can hear you now.
Excellent. Sorry about that. Very nice talk. Very interesting. Could you just say a few words about the pros and cons of taking this approach with respect to, say, quasi-Borel spaces as a sort of rival technology for semantics?
Right. Okay. Well, this one I think is very easy to understand. I think that our approach is very simple. However, okay, so as a con, so I have it basically here in my future work slide, right? So here I mentioned that we don't know if you can have a nice semantics using M if you want to talk about continuous probabilistic choice. Whereas the quasi-Borel spaces, I think that they are, there are papers which explain there how you can do continuous probability distributions. Yeah, but overall, I think that what we have here is pretty simple, and it integrates nicely with classical domain theory.
Okay, thanks very much.
Okay, so we'll quickly hear from Konstantin and then Paolo.
Okay, can you hear me?
Yep.
Right. So if we go back to your definition of the valuation, one of your first slides, so there is this modularity requirement there, right? So with this modularity, the definition of the integral becomes additive. So I'm interested in applications in social science and macroeconomics, cooperative game theory. So what happens if we change that the modularity requirement to supermodularity? Is there a snag in your proof? Is there how do we extend this?
What is supermodularity, sir?
So the same equation as the modular, although with an inequality instead of equality.
Ah, okay.
So the integral becomes a Shaikh non-additive integral.
Okay. Well, I have not really thought about this, but I think like a lot of the proofs are probably going to break.
Okay. Yeah, thank you.
Paolo, go ahead. Can't hear
Hey,
you.
Paolo.
I can't hear.
There are a couple more questions in the audience if you want to take them. Oh yeah, we can hear you now.
Yeah, go ahead, Paolo.
Sorry, I was saying very good talk. So about the Jung-Tix problem, have I understood correctly? So V is strong for the CPOs, but the commutative diagram that makes the strength commutative has been proven to commute only for the case of domains. Is this the problem?
Well, it has been so. Okay, so where's the Fubini equation here? Okay, so here, if you choose D and E to be domains, okay, so this holds. This is true. But this equation here also holds if D and E are DCPOs and the valuations are simple, for example. Okay, so you know it's like there are many special cases where you can prove this equation holds, but in general, unknown. Okay, so for the Untitled problem, so if you choose D and E to be domains, then okay, you get this, it is true. But then you have the problem with Cartesian closure. So because domains are not Cartesian closed, now you have to find a subcategory which is Cartesian closed, and this now becomes very difficult. So there are known Cartesian closed categories of domains, but then the valuations monad does not restrict to those.
Okay, so the problem is showing that equation holds for the CPOs and generic valuations.
Yeah, but this is the above problem.
Yeah, the simple one. Yeah.
Yeah. So in general, if you can prove Jung-Tix, then semantically you will be in a very good position, because then you will have a lot of structure, because you know each domain has more structure than a DCPO. So if you prove this, then you're in a very, very good position to do semantics.
Thank you very much.
Sure.
Thanks, Paolo. So I think we better move on to the next talk. Perhaps if there are other questions, they can be dealt with by email. So let's once again applaud the speaker, Vladimir, for a terrific talk.
Thank you.
And we'll let Tobias get set up now. Okay, could you say something, Tobias? So we can see your slides fine.
Somehow, yeah, sorry, my Zoom somehow disappeared when I was sharing the slides and I couldn't unmute myself. But now it should work.
Oh,
You see the slides?
Yep, everything's good.
All right, good, cool.
You ready?
Thanks. Yeah.
Okay. So our second speaker of this session is Tobias Fritz, who is speaking about a paper by himself, Tomáš, Gonda, and Paolo Perrone, called De Finetti's theorem in categorical probability. Go ahead, Tobias.
Yeah, right. Thank you. So yeah, Vladimir's talk was sort of very concrete and looking at concrete measure theoretic and topological objects. And so now what I want to do is in some sense on the other side. And I want to use categorical probability ideas in order to develop some probability theory within that. And in this particular case, sketch the statement and maybe a little bit of the proof of a very classical probability theory result, namely the De Finetti theorem. Okay, so but before that, I mean, yeah, some of you may already have seen the slide a couple of times in various versions. So there's a list of papers now, and today I'll mainly talk about the last one on sort of synthetic probability theory. I'll say a little bit about what I mean by that in a second. And so these are sort of this categorical approach based on these particular kind of categories, I think started, let's say, mainly with this paper of Cho and Jacobs. And then since then, yeah, there's been a number of things that have been developed within that framework. So yeah, my goal is to state and prove a classical theorem, and I'll do so without actually talking about numerical probabilities, but only talk about or do this based on a certain categorical system of axioms, which is more like saying how probabilities behave instead of saying what probabilities are. So in some sense, it's somehow analogous to the distinction between abstract algebra, working with and proving theorems about rings and fields, as opposed to working with concrete number systems, which are instances of those abstract algebraic structures. Yeah, so I guess in this audience, I don't have to say much about symmetric monodal categories and string diagrams, but so we're going to be working with, as the basic setup, a symmetric monodal category. And in this context, you're supposed to think of a morphism in that as a sort of probabilistic function. So giving a random input for any sort of output. So as particular examples, we can take Vladimir's Clay categories, for example, Clay category of a commutative affine monad on a category with finite products. This sort of thing will do for what I'm going to, the basic definition I'm going to present next. So now, well, we used a lot of string diagram calculus, and obviously I don't have to say much about this. And also the proof is very much string diagrammatic. Just having a symmetric monodal category is not enough to talk about probability theory, as it turns out, and we want some additional pieces of structure which somehow model the idea of information flow and the concepts of copying and discarding information. And so that amounts to saying that every object should have additional pieces of structure, of course, coming in the form of a co-multiplication like this. So my string diagrams go from bottom to top, x to x tensor x, representing something like copying values of x, and correspondingly a discarding map from x to the monodal unit, which we think of as discarding information. And then these should form a commutative comonad structure in every object. And then we get this definition of Markov category, named after the idea that the morphisms behave like Markov kernels. And there's an additional requirement that this needs to interact well with the monodal structure, but I won't go into the details of that for now. It's kind of the obvious thing. And well, this equation at the bottom, which is in some sense a normalization of probability, saying that, well, when you discard the output of a probabilistic function or process, then that's equal to discarding the input to begin with. So as far as the semantics is concerned, how do we, what kind of categories have this kind of structure? Well, our intended semantics, in a sense, is Borel stock. So the category of standard Borel spaces is objects. Those are particular measurable spaces, which can be proven to come only in these particular isomorphism classes. And then measurable Markov kernels is morphisms. So these are basically the measure theoretic generalizations of stochastic matrices. And well, we use ordinary product for the monodal structure. And then this turns out to satisfy all of the axioms that I'm going, additional axioms within this formalism that I'm going to mention in the following. And it's also, well, the classic category of the Schiri monad on these standard Borel spaces. But this is just an instance of a general observation that whenever you have a commutative affine monad on a category with finite products, for example, Vladimir's Clay category, or Clay categories as well, then it's Clay category as a Markov category in a canonical way. So before, I want to get to the Finetti theorem, but in order to be able to state it, I need to introduce a few more definitions within this framework. So obviously, you want to talk about particular morphisms that do not do anything random, but processes that are deterministic. And so this is formalized by this equation here, which I mean, certainly goes back a long way and has been used in various contexts and in variations on this. But so the way to think about this equation is that on the left, what we do is just to copy the input and then apply two independent copies of the process f to those copies of the input. And if f does something random, then the two outputs that we get on the left can be different. While on the right-hand side, we just apply f directly and then copy the output. So here it's guaranteed that these two outputs are equal, intuitively speaking. And so if f does something actually random, then this equation will not hold. And conversely, by the same reasoning, essentially, we can argue that, well, if f is deterministic, if f is deterministic, then this equation holds. And then purely string diagrammatically, it's pretty easy to see that deterministic morphisms form a monoidal subcategory. And then we can also show that the monoidal product on the subcategory is actually a Cartesian. And now in many cases, so for example, in the case of Borel stock, where it's a Kleisli category, and now as part of the assumptions in the Finetti theorem, I'm going to have this notion of representability, which is essentially saying that a given Markov category is a Kleisli category of a commutative monad on the subcategory of deterministic morphisms. And it turns out that this is actually a very simple property of the Markov category C itself. Namely, just this representability, that basically what this is saying is that the inclusion of the subcategory of deterministic morphisms should have a right adjoint. And this makes it into a Kleisli category, and then we can basically show that it is Kleisli category of the resulting of the induced monad on C det. We actually need something a little bit stronger called almost AS. So AS stands for almost surely, as the sort of thing that almost surely or almost all the time appears in probability theory. That this representability respects almost sure equality in a sense. But yeah, I think I'm going to skip the details of what this means for the moment. And yeah, so intuitively, this makes Px this representing object into the space of probability measures on X, because, well, now intuitively, a morphism or a random process from A to X is the same thing as a deterministic function from A to probability distributions on X. Because a Markov kernel or such a stochastic function just sort of outputs a probability distribution. So in that sense, it's a deterministic map. And if we look at a co-unit of the adjunction, then that corresponds to a morphism. Again, think of it as a Kleisli morphism like this, which takes a probability measure and then outputs a random element of X, so to speak. And we hence think of this as sampling from the given distribution. And so this just under the Kleisli, under the adjunction, this just corresponds to the identity on Px. So it's kind of a trivial thing, but it has this useful interpretation in terms of sampling. And yeah, so now what the Finetti theorem says is actually a very particular kind of representability in a sense. Namely, what a statement is that Px, well, it's not just an arbitrary representing object like that, but it can actually be constructed as a certain kind of limit. Namely, if we look at x to the n, So, well, I haven't formally defined what this is, but this is something like, well, this is basically the co-filtered limit of all the finite tensor powers of X. And so this is something like, yeah, I mean, a space of sequences from X. And the Finetti theorem now essentially says that in the Markov category or the classic category C, Px is the equalizer of all the finite permutations on this object. So we have this permutation group just permuting the tensor factors acting on this object, and then Px is the universal thing with a morphism into this x to the n, which equalizes all these permutations. And the universal arrow is given by sampling infinitely many times. So if we have a probability distribution, we draw countably many samples, then we basically get a random sequence, which is permutation invariant, obviously, because all the samples are independent and identically distributed. And conversely, if we have, well, basically, if we have a probability measure on x to the n which satisfies permutation invariance, then it actually corresponds. So this would be now a morphism from 1 into x to the n. If this one satisfies permutation invariance, then it corresponds to a morphism like this, which is now which corresponds to a random measure on x, because it's a Kleisler morphism to px. So it's really an element of ppx. So a bit more intuitively speaking, one can interpret this as saying that a probability distribution is roughly the same thing as a prescription for how to sample from it. You can define a map to px by defining a permutation invariant map to x to the n, and this is roughly a prescription for how to sample. The difficult part of proving this theorem, so this theorem applies to Borel-Stock. And I mean, the classical version of the Finetti theorem is in this case. I mean, there's a couple of variations on it, but let's stick with this one. And this is actually not so easy to prove. And even still nowadays, there's occasionally new proofs appearing in the literature. There's a recent new proof using non-standard analysis, for example. So now our point is that we have a proof in terms of Markov categories and entirely categorical axioms. And because of this, because it's this more high-level language and formalism, it does not need to go into the details of the measure theory anymore. I think we can claim that this is the most intuitive proof that exists to date. And so maybe I can say a little bit about that. But so here's the theorem. Yeah, it's about a Markov category C. And then again, well, we need a bunch of additional assumptions, axioms. One of them being this almost surely compatible representability that I had mentioned. It's basically a Kleisler category of a nice commutative monad. We need to be able to talk about these countable powers, this x to the n, or more generally about countable tensor products. And this is encoded in the existence requirement of what we call Kolmogorov products. So these have a certain, basically universal property. And maybe the most important assumption is that we require the existence of conditionals. So this is a categorical axiomization of the possibility to form conditional probabilities. And this seems to be really somehow what narrows it down a lot to actual measure theoretic probability. Yeah, and so these are purely categorical statements or assumptions. And then the theorem says that, well, whenever you have a permutation invariant morphism whose codomain is such a countable Kolmogorov power, and if it's invariant on the finite permutations of the factors, then it arises from an actual morphism to Px by composing with this countable sampling map. So just like on the previous slide, this is the existence part of the universal property. And it's the difficult part, and somehow, yeah, it's a little strange that we can prove this difficult part, but at least so far we have not been able to prove the simpler part, which is the uniqueness part of the universal property. Yeah, so, well, one could hope that now, given that this is a categorical statement, that one could actually also now would have a more general theorem that it would apply to other instances. And we still hope that this is the case, but so far this has not panned out, and that we know of no other non-trivial Markov category which satisfies all of these axioms or all of the assumptions of the theorem. And this is somehow quite intriguing. I mean, putting it positively, it seems that these conditions narrow things down quite a lot. Okay, so I think I should actually sort of also be heading towards the finish line, but to maybe give a little bit more intuition about what this means. Suppose that I hand you a coin, and while you don't know what the bias of the coin is, but I ask you or give you the possibility to bet on certain outcomes. Then, for example, if we flip the coin 3 times, how much would you bet on the outcome being heads, tails, tails? Well, we can't really say. There is no unique answer. There's no definite prescription because the bias is unknown. And so as a Bayesian, you might have some prior or over the possible, over the space of biases. So we can't really say what the probability or how much you would be willing to bet. But surely it would be the same as how much you would bet on the outcome being tails, tails, heads, because, well, at least you would trust the coin to be, the coin flips to be independent and identically distributed. So therefore, this motivates the permutation invariance for your bets. And that means that we are in a situation where the Finetti theorem applies. We would have a permutation invariant distribution on the space of sequences. And then the theorem says that, well, this corresponds to an actual measure on the space of biases. And for a Bayesian, this is exactly the prior. So this is somehow the significance of the theorem. Yeah, I can go into the details of the proof if anyone wants to see something, but just to outline sort of the fact that the proof is still not easy, and it is string diagrammatic. And yeah, I mean, I guess sometimes, especially from people in other communities, that may hear the criticism that, I mean, the string diagram stuff is all pretty trivial, but this one is definitely not, and we actually spent a long time on it, and it wasn't clear if it would work out at all, and so it's a number of lemmas and things, and I can give at least show sort of the final part of the proof, or the main thrust of the proof. So which is in the case, suppose that we're only looking at the case where our permutation invariant morphism is a state, so that its domain is the monodal unit I. And then, well, it turns out to be, so I haven't actually explained what these things are, but then, yeah, we basically want to prove an equation like this. And now this this double wire denotes really now our infinite tensor product. So the double wires really denote infinitely many wires. And it turns out to be enough then to prove this equation, and where P given tail is sort of conditional, a certain kind of conditional of the state P. And yeah, we basically have then a string diagrammatic induction proof for this equation. based on the previous lemmas. And yeah, so I'm not sure to what extent this is interesting, given that I haven't shown the previous, don't have the time to show the previous items, but just to give a rough idea of what it looks like. Okay, so I hope, or I've been wanting to demonstrate that this framework of Markov categories is an emerging framework for doing probability theory synthetically, which means, well, without talking about probability measures at all anymore, other than in the proofs that the axioms hold. And so we have a bunch of synthetic versions and partly generalizations of classical theorems of probability and statistics. So there were theorems on sufficient statistics were the first ones, like a version of the Fisher factorization theorem. We also have 0-1 laws. And now, yeah, today I've been presenting a little bit about the Finetti theorem on permutation and variant distributions. And yeah, what I would really like to be able to do is to do the same thing with the law of large numbers, because that is such a both basic and central theorem of probability theory that and anyone who wants to claim to have a sort of axiomatic approach to probability needs to be able to reproduce that. And so this is something we don't have yet, but we can hope to. At least it seems that if we turn a little bit of that into a definition, I mean, often one should expect sometimes we need to turn theorems into definitions, then it seems that we can do something in the direction of the law of large numbers, but this is still kind of work in progress. And it seems that there's connections with ergodic theory. So it seems that we can also that this formalism is particularly apt at good for talking about stochastic dynamical systems. But yeah, so in parallel to doing this stuff, which is purely synthetic, so taking place at the purely categorical level, we also aim at a better understanding of the semantics and of sort of the landscape of Markov categories. And a central question here is, I think, how common are Markov categories with conditionals, where one can form conditionals? So Borel stock is one, but in terms of other ones, it really seems to be a tricky problem, especially in combinations with the other axioms. All right, yeah, so I hope that this gave a bit of a flavor, and I'll stop here, and thanks for listening.
Let's thank our speaker. I think we're going to have to skip questions to get on to the next talk. So perhaps
one in the lecture theatre from John van der Westering.
Okay, we'll do one question.
Hey, yeah, I was wondering, because a Markov category was a very general structure, and you need some additional structure to actually prove this thing. And you also have a couple of different.
Well, we don't need additional structure, only additional conditions or properties.
Yeah, yeah. So, and also you have some other results in synthetic probability theory. So I was wondering, do you feel like you're closing in on what is the correct setting to do synthetic probability theory in, like a Markov category with this additional stuff? Like, do you feel like there's something to be said there?
Not yet, and in particular, I would say that there probably isn't such a unique thing as synthetic probability theory, and there's probably various levels. And I would say the analogy is maybe roughly like with a homotopy theory and homotopy type theory. So homotopy type theory, I can say, somehow synthetic homotopy theory, but it still has also many other, I mean, applies and it has a much broader semantics. And so everything that you develop synthetically in there applies more generally, but somehow in some sense, it seems to get pretty close to ordinary homotopy theory, but not all the way there. And maybe there are other synthetic approaches that get closer. And so I think the same is true here for probability theory. In particular, so Alex Simpson, for example, seems to be working on a synthetic approach that is much closer to measure theoretic probability.
Okay, thanks.
Okay, let's thank the speaker again and move on to the next talk. Okay, Razin, are you ready? Can you say something? I can't hear you. So I'm not hearing anything.
Hello?
There we go.
Okay. All right, I'm ready.
Okay, good. So our next speaker is Razin Shaikh. I apologize if I mispronounced that, who's presenting on a paper with Leah Ye, Benjamin Rodatz, and Bob Coecke, and the paper is called Composing Conversational Negation. Over to you.
Okay, hello everyone. Today I'm going to talk about conversational negation and how to compose it. So first I'm going to give a brief overview of what categorical framework we work in, and then I will talk about conversational negation of words, sentences, and evolving meanings. So what is compositional distributional semantics? So in distributional semantics, we have words that have meaning, and this meaning could be vectors or density matrices or any other representation. But they form a category called they form a meaning category, and this meaning category happen to have a compact closed structure. So now, but still, this category has just a bunch of words. There is no connection between them. So that we look at another category of grammar. So it could be pre-group grammar or any other representation of grammar. And this grammar category also has a similar compact closed structure. So to combine grammar with meaning, we simply take a functor that goes from grammar to meaning. And by doing that, we get this. So if we know the meaning of Alice, love, and Bob, we can combine them in this compact closed structure using grammar to get the meaning of the sentence Alice loves Bob. So here you can see that there is one wire coming out of this wiring that gives the meaning of the whole sentence. So in DiscoCat, we can go from meaning of words to meaning of sentences. Now, the natural question to ask is, why do we stop here? The DiscoCirc says, all right, let's compose sentences. And by composing sentences, we get the meaning of the entire text. So in essence, there are like two main components of this in DiscoCirc. So we have meaning states, and they carry the meaning through the wire. And instead of having a wire representing the sentence, we think of sentence as a process that updates the meaning of other words. So here you can see that the meaning state love updates the meaning of Alice and Bob. And we can have more than one sentences that updates the meaning further. So that's the basic framework of DiscoCirc. Now the question is, how do we model conversational negation in this framework? So first of all, what even is conversational negation? So let's say I say the sentence, this is not a hamster. What am I referring to? Well, if I say this is not a hamster, this is a planet. This sentence is grammatically correct. However, there is something odd about this sentence. Like why am I referring to not hamster if I want to talk about planet? On the other hand, if I say this is not a hamster, it is a guinea pig, this makes complete sense. Like this is a very sensible sentence. So if we want to negate hamster, we can't simply do logical negation, because logical negation doesn't know the difference between a planet and a guinea pig when you do it on not hamster. So in doing conversational negation of hamster, we want to capture this human understanding that not hamster is probably guinea pig and probably not a planet. So given a word W, we want this process called CN word, conversational negation of word, that tells us that conversational negation of what the conversational negation of that word should be. So how do we create this box? Well, we first start with logical negation, because it at least tells us that, okay, what not hamster is, even though it may not have proper human understanding. And after that, we say, to give in the worldly knowledge and the worldly understanding that human has, we update the meaning of this logical negation through worldly context of that word. And so this is the work that we did in the SemSpace paper that came out a few months ago. And we also performed experiments using this framework. And the basic summary is that it works. But before I go on, I first need to explain what this worldly context box is. So to calculate this worldly context of a word, we use something called an entailment hierarchy. Entailment means the is a type of relation. So what is so this is the entailment tree I've taken from WordNet. So hamster is a rodent. A rodent is an animal is some entity. Now, if I want to say not hamster, I look at this entailment tree and say, okay, something that's not a hamster could probably be a guinea pig, another rodent. But it's also possible in less proportion that it could be another animal, such as a dog. In some very weird scenario, it might even be a planet. So to calculate worldly context of the word, we look at this entailment hierarchy, and we go from the bottom of the hierarchy to the top of the hierarchy, and we create a mixture where the entity at the bottom of the hierarchy has weighted the most, and we reduce the proportion. So once we calculate this worldly context for the word, we update the meaning of logical negation through this worldly context, and that's how we get conversational negation of the word. All right, so that's how we do conversational negation of word. So the natural question to ask is, how do we extend it to sentences? So before we do conversational negation of sentence, we need to understand how negation plays a role in sentence. So let's look at an example. If I say, Bob did not drive to Oxford by car, what does it mean? Well, there are multiple interpretations that could be correct for this sentence. So if I say Bob did not drive to Oxford by car, I could be referring to like someone else did. Maybe Alice went to Oxford. It's also possible that Bob took another vehicle to Oxford and not a car. And in some cases, Bob did not drive to Oxford by car, could also imply that Alice drove to Oxford by van. Even though this last interpretation is less likely, it is still possible. So there are a couple of observations that we can make here. First, the negation in a sentence could attach to any of the word in the sentence. In fact, any subset of words in the sentence. Secondly, not all interpretations are sensible. Some interpretations make more sense than others. So when we want to do conversational negation of sentences, we want to capture this ambiguity that's present in the sentence. So now suppose we have words W1 to Wn in a sentence that goes into this conversational negation of string box. We first want to consider all the cases where one of the word in the sentence is negated. So that's the first line. Then we also want to consider the case where two words in a sentence might be negated. So we consider all the cases where two words are negated, and so on. Another way of saying it is, if we have a set of words and we can take any subset of this words and we call that subset a negation set, and we negate those words in the sentence, and we sum over all possible negation set. Moreover, each of the negation set has a weight associated with it, which indicates how likely that interpretation is correct. So here the negation set S prime has the weight P of S prime. So, all right, now let's look at a concrete example. Suppose I have a sentence, Alice loves Bob, and I say, I want to negate it. So I do Alice does not love Bob by applying this box. And this is equal to the first term, which says, okay, the negation set is Alice, and we negate Alice, and it has a weight associated with it. And the second term is where love is negated, and so on for all possible combinations of negations. So, all right, we can do conversational negation of sentences. But the bigger question here is, how do we know what is the right interpretation? And to calculate that those weights, it tells us which is the right interpretation. It's not simple. So, because there are many sources of context that tells us what is the right interpretation. So first, the text that surrounds a negated sentence also informs us what the correct interpretation should be. So in the paper, we give intuitions of how surrounding sentences could inform the negation, the right interpretation of negation. But that's not enough. In speech, intonation also plays a role. So if I focus on one particular word, that could be the target of negation. Environment is also very important because words mean different things in different environments. If I say category here, it means something different than if I were to say someone outside ACT. All right. Finally, the knowledge of the world is also needs to be taken into consideration because we don't want to give interpretations to the sentence that are not sensible. So we have done some work on deriving context from text, but still more work needs to be done here. Right. So now we'll talk about how to do conversational negation of words whose meaning changes throughout the text. What do I mean by evolving meaning? So suppose I have this sentence, Alice is a mathematician. So when you first see the sentence, we learn that Alice is someone who's a mathematician. But then I look at the second sentence in the text, I learn more information about Alice, that Alice lives in Oxford. So the meaning of Alice has been updated by the fact that Alice lives in Oxford. So now if I want to know who this not Alice might be, how do I do that? So if I ask you, if Alice did not write the paper, who did? And I want to find the negation of Alice, who is this not Alice? So suppose we have two other characters in the text. One is Bob, and Bob is a computer scientist who lives in Oxford. Another is Claire, who is a pianist who lives in Hong Kong. If I ask you who is this not Alice more likely to be, Bob or Claire? Well, I'm sure you would say that's probably Bob because they both live in Oxford. One is a mathematician, other is a computer scientist. So they have a lot in common. On the other hand, Alice and Claire are very different. So you're not likely to refer to Claire when you talk about not Alice. So how do we do negation here? So the key is let's look at the circuit of this text. So Alice is a mathematician. Alice lives in Oxford. The circuit looks like this, where first we update the meaning of Alice with the fact that she's a mathematician and with the fact that she lives in Oxford. Now this sentence we can equally say in one line as Alice, who is a mathematician, lives in Oxford. In this circuit, then the texts that have same meaning result in almost the same circuit. So you can see here that this is simply wires that are bended. So this gives us an intuition that if we have multiple sentences in the text that updates the meaning of Alice, we can simply think of that as one large sentence. And we already know how to do conversational negation of sentences. That's what we did before. So to conversational negation of Alice, we apply the same framework. And in this case, conversational negation of Alice could be, so here it could be negating the fact that she's a mathematician, or she lives in Oxford, or both. But this, which interpretation is correct, again, depends on many of the sources of context. So now we want to see if not Alice implies Bob, Moore, or Claire. So to do that, we'll just consider the case which could result in the best scenario for both Bob and Claire, and see what has better entailment. So the best negation set for Bob of not Alice for Bob is the fact that we are negating mathematician and we leave Oxford as it is because Bob also lives in Oxford. So now someone who is not a mathematician could very well be a computer scientist. So not a mathematician highly entails a computer scientist. On the other hand, Oxford is just Oxford. So Oxford almost certainly implies Oxford. So in this case, we have very high entailment. For the second case of Claire, the best negation set is when both mathematician and Oxford is negated, because Claire is not a mathematician and not lives in Oxford. So now we have not mathematician. Not someone who is not a mathematician could be a pianist, but there is not very high entailment or very big implication there. So I would say it's like medium entailment. On the other hand, not Oxford could be Hong Kong, but it doesn't really suggest us that. So in this case, the entailment would be low. So we can see that the framework that we presented here captures this human intuition of what the negation of Alice should be. All right, so how can we extend this framework in future work? So first, we need to figure out how to calculate the weights of these interpretations through different sources. We also would like to explore how to negate phrases. So here there's an example. This is not the key to the garage. So here the entire phrase, the key to the garage, is negated to get the meaning that this is a toy. And we would like to extend it to there. In this bigger picture that we want to build here is to develop the entire conversational logic. So we know how to do conversational negation. We'd like to explore how it interacts with conversational and, conversational or, and even quantifiers. And finally, we have done experiments for single words, conversational negation of single words in the SemSpace paper, but the experiments for sentences and evolved meaning still need to be conducted. Thank you.
Thank you. So let's thank our speaker before we get to questions. Okay, so we have a question from Zoltan.
That's right. Well, thank you. Very interesting talk. So in these examples you present regarding conversational negation, it seems like this is really about the grammatical category of focus. And well, famously in English, focus is expressed by like a pitch accent, and in the written representation, it's just not there, right? Yep. So you're somehow reconstructing it. But there are other languages where focus is marked syntactically. And indeed, there are some languages, Hungarian is certainly one of them, Turkish and Lakota, I think, are other examples, where these negations are largely, most of the time, unambiguous and can be figured out by purely syntactic methods. So my question is, have you looked at, or are you planning to look at experiments with, say, bilingual data sets, where you can deduce focus explicitly using one method and the other to validate your approach?
So the negation that we presented here comes from intuitions from psychology papers, and the work that has been done there, or the work that I looked at, was about languages like English where there is ambiguity. But if there is, there are languages where it's not ambiguous, I think that's definitely worth exploring. But yeah, we haven't really done that or thought about that.
Okay, that makes sense. Thank you. Just it might imply something about your grand challenge as well of formalizing sort of mathematical logic, because it might be an uphill battle if that's language dependent, right? If this is not a linguistically universal. Yeah. Anyway, thank you for your answer. So makes sense.
There's one question in the lecture hall. We can take that.
Okay, go ahead.
Thank you. This was super interesting. I'm wondering, what is the Alice vector? What's the Bob vector? I've been asking this myself because you're updating the meaning of Alice and Bob and Claire. But how do you, where do you start from? If you say, like, there's a mathematician who lives in Oxford, there's probably a mathematician vector that you can derive from corpus. But But Alice and Bob are so relative. So have you thought about how to where to get those vectors from? Or should they even be vectors? Is that also a question?
So here the idea was that we should start with, so initial vector of Alice should be something like the preconceived notion that we have when we hear the word Alice. So there's something that we know when we hear the word Alice, that Alice is probably a woman, probably lives in in certain parts of the world. So in DiscoCirc, the idea is when you initialize Alice, you initialize using the state that has notions of Alice that is kind of very basic, and then you update the meaning of Alice after that. So yeah, how do we know what exactly the vector must be? I think it's very similar to other words, because like when we think of Alice, we already know some very basic information about her, and we should always just start with them, that information, and then update it later.
Thank you. Thank you.
Are there any other questions? Or
Yes, there's one more in the lecture hall.
So I think I got the idea of how this negation was happening, that you're saying if you say not something, it's the things that are closest to that, but then also not as the exact thing. I think the thing that's confusing me is what exactly is this black box doing that somehow seems to just merge meaning. So this black box in the bottom right.
Oh, right. So this black box corresponds to meaning update. So there are many different operations that do meaning updates, and there is active research on that, on what works best. So one is like the phasor, which corresponds to the Bayesian meaning update. There's also first. There are many ways of combining them. So one could be just simply matrix multiplication. But what exactly updates meaning? I think that's very experimental in the sense that you need to see what works best. And there are many different proposals for this.
Are there categorical properties you want of this meaning update? Is it like a monoid or something else? Or
well, when people first started, they started with this meaning update to be a spider, the Frobenius algebra. But then they soon realized that well, if it's just a spider, Frobenius algebra, it can commute, and we don't want it to commute. So yeah, we definitely don't want it to be commutative. But there are many other properties that I think that are explored in the meaning update of density matrix paper by I think Konstantinos and Bob. But yeah, there are certain properties that we wanted to have. For example, it should definitely not commute because Alice is a mathematician and Alice lives in Oxford. Here, if you replace the sentence, it's fine. But in many cases, it would not be fine. For example, if you are building a recipe of something to eat, like you can't just change the order. So that's one thing that I'm aware of, but there must be others as well.
Okay, thank you very much.
Is that everybody?
Yep.
Let's thank our speaker again for an excellent talk. And that concludes our morning session. I want to thank all three of our speakers and all of the co-authors who didn't speak, as well as the excellent staff at Cambridge for keeping this session running so well. I'm going to ask Jamie to announce when he wants to start up again.
In about 20 minutes, I think, past.
It is.
Yep. Great.
Yeah, let's start again on time, please. Well, we got about 20 minutes. Okay, thanks a lot, Rick.
You're very welcome. Thanks, everybody.
Don't forget to launch breakout rooms.